In the first set of videos looking at reactions of aromatic compounds, we're going to start by actually looking outside the benzene ring itself, towards the benzylic position. We're going to review a reaction we've already seen, but put it in a new context, that of aromatics, and we'll learn another new one. So, when we consider the benzylic position, we must remember that the benzylic position is here. It's not attached to it's not the benzene ring itself, but it's in fact the one carbon off the ring. So another benzylic position would be this one. Whatever those R groups happen to be doesn't matter, but a benzylic position is one adjacent to a benzene ring. So it's coming off of it. And it's somewhat analogous, right, to an allylic position, which is right next to a double bond. But a benzylic position is a little special because you now have an aromatic system at play here. And so we might abbreviate this, by the way, AR. AR stands for aryl, which means an aromatic group. Typically that's benzene, which we abbreviate PH, right? But it could be a generic aromatic group. It could be something like indole, for example, or pyridine. It doesn't quite matter, but you might see AR. It doesn't mean argon, of course. Argon is a noble gas. It's not going to react with anything. But you might see it as an AR group, which will be meaning aryl, ARYL, which stands for an aromatic substituent. So this position here would be benzylic. And so if we consider what we can do at the benzylic position, one reaction we've seen before is using NBS and UV. And in doing so, we will selectively brominate the allylic position. And of course, since it will undergo a radical mechanism, that radical adopts an sp2-like conformation. And as a result, we will get a racemic mixture at that position. We can either, the radical, as we know, rapidly flips up and down. So it inverts the stereochemistry as well as retains it. So we end up with a racemic mixture, as we do with many reactions, right? So this is very much the same as an allylic process, right? We just have a more stabilized one. So NBS will selectively brominate a benzylic position over any other. Remember that NBS is the following compound. It's N-bromosuccinimide. That's what NBS stands for. So NBS. That's NBS. And remember, this is a radical process, so we will undergo a radical reaction. You can review the mechanism from last semester, but the mechanism is not terribly important here. Suffice it to say that you can use NBS to selectively brominate. And as we know, once we have a bromine, we can do all sorts of fun things. We can substitute at that position. Maybe we could turn it into an alcohol and then oxidize it, and now we have a ketone. Or you can turn it into an alcohol and use that as a nucleophile for something. Deprotonate it, use it in a Williamson ether synthesis. Or you can take that bromine and replace it with a different nucleophile, say a nitrile. Add a cyanide group there. And then you can, well, we haven't learned reactions of nitriles yet, but then you have new things you can do. So it's a way of activating that benzylic position, which then we can use towards other reactions. So remember that just kind of any just halogenated compound, we can do all sorts of, this thing is great for substitution. And it's a, since it is a secondary, presumably a secondary, in this case it is, a secondary benzylic position, it's particularly good for SN1 type reactions, or even E1, so we can make it into an alkene. So this is great for substitution and elimination, right? At that benzylic position, we can say, aha, I'm going to take my benzyl bromide. And well, this case we can't eliminate. Here, we'll make it slightly more fancy. We can treat this with a base, right? How about sodium methoxide and heat? Now we've got an alkene there, which we can do alkene reactions with. Or you could even do a Diels-Alder with that, by the way. Or we can say, okay, well, I want to take that same compound and let's go ahead and substitute in an alcohol there. Why don't we do low temperature to avoid any elimination? And then step 1. Step 2, let's go ahead and add some oxidizing agent. How about DMP? In doing so, we'll now have a ketone. We'll have acetophenone. So don't forget all of the reactions we've studied last semester. So alkyl halides are very useful in reactions. We can do all sorts of stuff. If we want, we can turn this into an alcohol on the far carbon instead. Right? You can do that with BH3 and THF followed by hydrogen peroxide and sodium hydroxide, right? Hydroboration oxidation. So don't forget all of those fun things too. Our regiochemistry and all that still are very important here. So hydroboration oxidation. Again, same thing. Don't forget all your previous reactions. So basically NBS is a tool for us to selectively get that benzylic position a little bit more reactive, so now we can do other stuff. And so all of this is very important for when we're looking at synthesis of things. So if you want, we could start with, if we wanted to get from ethylbenzene to the one with the alcohol, we've already looked at this, right? I mean, it's weird to activate that position, but we know we can work with that position, the benzylic one. We can convert it first using NBS and UV. We can then, once it's brominated, that puts the bromine here, right? Puts it on the allylic position. We can then eliminate it using an E1 or E2 process. Either one would work just fine. And again, you'd probably want to do that by throwing a lot of heat on it to favor elimination. And then if you wanted, you can use BH3 and THF, followed by NaOH and hydrogen peroxide. And that would give us this product, right? So it's another step we can use. These are all, what was OCHEM 221 reactions. So don't forget all of those. We have lots of other stuff. And if we wanted, we could make that into an aldehyde and then add to it with a Grignard reagent. Have all this fun, right? I mean, that's the idea here. So you can't forget all of the previous stuff. Go back, look at the old videos. They're on my YouTube channel. Or you can look in your book, of course. Okay, so that's one thing we can do. The only other reaction at the benzylic position we're going to look at is oxidizing it. If you use something like dichromate, a strong oxidizing agent, or KMNO4, another strong oxidizing agent, what will end up happening is you will end up getting a carboxylic acid out. And interestingly, it doesn't matter how many carbons you have on your benzene. You could have 200 carbons here. Put them with the same reagent, and you will cleave off everything, leaving you with a benzoic acid of some sort. So anything that's not a fully tertiary position, I should mention that. So just a methylbenzene or toluene, as we call it, right? That will undergo this reaction too. You'll end up getting the carboxylic acid. You'll just oxidize it. So you can fully oxidize that benzylic position. So any non-tertiary benzylic position becomes a carboxylic acid. Right? So a tertiary one, you don't have the room to do that. So something like this T-butylbenzene, if you try and go ahead and use your dichromate with that, you get no reaction. I'll write that out. You get no reaction. It has to be something that's not, did I say tertiary? I meant quaternary. I know how to count, I swear. Sorry. So non-quaternary positions. Tertiary positions are fine. You can oxidize them. So let's show what one that might be. Like isopropyl benzene, tertiary, right? That benzylic position is tertiary. Treat that with either of those oxidizing agents, you get a carboxylic acid out. The rest of it doesn't matter. Like with before, even if you have 20 carbons stuck on your benzene, as long as that benzylic position has a hydrogen, meaning it's not quaternary, it will react and it will cleave off everything, forming a carboxylic acid. And so we can see here that it doesn't matter. Secondary, really long secondary, primary, tertiary, all of these will react with a strong oxidizing agent, and you'll end up with your carboxylic acid. Remember that these two oxidizing agents are interchangeable. I will write that out here. These are interchangeable. And don't forget that these also react with other things, right? If you take KMNO4 in the presence of an alcohol, as in an sp3 hybridized alcohol, you'll oxidize it, right? If you have hydrogens nearby. So don't forget that if you have something like, let's have something like this. If you treat this with KMNO4 or sodium dichromate, potassium dichromate of any sort, you'll end up cleaving any non-quaternary benzylic carbons. So that's the one on the top. And don't forget that, so this position here is quaternary, so we can't oxidize it, so it's safe, but we have that alcohol. The alcohol will be reacted as well. So, as always, we have to pay attention to other groups that may be sensitive to these reagents. So remember that alcohols, alkenes, alkynes will all react with potassium permanganate or sodium dichromate. And so you've always got to pay attention to those as well. So as a result, it's adding another set of tools to your toolbox, which is ever growing. You'll have hundreds of reactions by the end of OChem. And it's still very important that you keep these in mind. So keep a flashcards, keep like a poster going or something of all the sets of reagents and all the things they do. So this is the first set of things that we're adding to our toolkit. So NBS and a strong oxidizing agent will either brominate or oxidize your benzylic position.